Hi everybody, this is David Paul. So we're here to have a webinar on pH and ORP troubleshooting. It will be me talking a bit and then Sherlyn Marlowe from Yokogawa doing the major portion. So most of you know about Yokogawa, a huge company all over the world, does many more things than you and I probably know about. We may know more about the instruments, but they have all kinds of different business segments and basically in just about every industry that you can name. I'm president of David H. Paul Incorporated. We've been training and consulting since 1988 in a lot of different technologies. We offer a lot of different training programs, and we also provide technical services and consulting. So this is part of 5 webinars. So we're calling this a mini series on instruments and PLC basics. And today we're on number 3. If you didn't attend either 1 or 2, you can go on our website and you'll see that here in a bit. And you can see those pre-recorded webinars. So this is a 45-minute presentation. I'm going to give a brief introduction, and then Sherlyn is going to give the bulk. We'll leave 10 to 15 minutes for question and answers at the end. Just type your questions into the question chat box. This presentation is recorded, so it's going to be available, and you'll be sent a thank you email tomorrow or Monday, and in it you'll have a PDF of this presentation, and you'll also have a link to the recorded webinar in case you want to look at it again. So just to make sure you realize that Yokogawa and David H. Paul Inc. do not have a financial relationship. We're not endorsing each other's products. We're simply offering this webinar because it's a topic that's of interest and value to both of our customers, our clients. So I've been in water treatment since 1977 and training and consulting at hundreds of plants since 1988. And Master of Science degree in microbiology, and also 4th level certified through David H. Paul Inc. Sherlyn is the process liquid analyzer product manager for Yokogawa. She's been with them for 9 years, has some really good previous experience, and a Bachelor of Science in Biochemistry from Kennesaw State University. So again, input your questions at any time during the presentation, but we'll cover them right at the end. Sherlyn will say the question and then give the answer. Any questions that you ask and they don't get covered by the ending time, you'll receive the answer by email, but then we also edit the question and answers to the recorded webinar so that you can get those question and answers later. So I'm just going to do a real brief overview and an example of pH troubleshooting, and then another brief one on ORP troubleshooting. If you want a real excellent review of the pH basics, then go to that first webinar. And again, you're going to receive a PDF of this tomorrow, so you'll get this link tomorrow, or Monday, one of the two. All right, so the example that I'm going to use, I think, is a very common example. We'll look at RO chemical cleaning and look at pH troubleshooting. So here's a real common standard operating procedure. You mix up the cleaning solution, you circulate for an hour, you soak for an hour, you circulate for an hour, you flush, you're back into normal service. So that's a cleaning. Well, some of you do, some of you don't, but we recommend that you monitor the cleanings. And in this, there are certain things that are very important to monitor. We won't get into the details of that. And then also there's a column that shows the guardrails. You know, don't go below this or go above this pressure or temperature. And then we recommend every 15 to 30 minutes you're taking data and making some notes as needed. That way, you know, you can really monitor and see what's going on. So let's just say that we did this cleaning and we're tracking normalized permeate flow, which we should be. And so we cleaned when the normalized permeate flow dropped 10 to 15%. But then after the cleaning, we see that we only gained back about 50%. We didn't go back to new or near new performance. So why? Well, we could do some troubleshooting. Some things that can happen is we waited too long to clean. We won't talk any more about that. We're only going to talk about pH at this point. Cleaned it too low a flow rate, too low a temperature, didn't clean long enough, didn't replenish cleaning chemical, and that's really what we're talking about here. So if we look at the data for this cleaning, we started out at a pH of 11, and by the end of the cleaning, 3 hours later, we're at a pH of 9, and we didn't add any chemical to it. So remember from 2 webinars ago that pH is logarithmic. The pH scale is logarithmic. So each pH unit is a 10-fold change in hydrogen ion concentration. So we saw this 2 webinars ago. We saw the hydrogen ion concentration in moles per liter and also the hydroxide, but we won't talk about that today. And then on the far right, we see the pH scale going from 0 to 14. So every pH change is a 10-fold change in hydrogen ion concentration. So if we started out with a pH of 11, we would call that's our new solution, that's our 100% strength. What's the strength of the cleaning solution when we hit a pH of 10? Well, again, it's logarithmic, so we only have 10% of our cleaning solution left. And if we wait until it hits a pH of 9, what strength of cleaning solution do we have? Only 1%. So this is an example of using pH for troubleshooting. We should have added more cleaner. And that might be the reason, or at least one of the reasons, why we didn't clean this back to new performance. And then finally, just a quick one on ORP troubleshooting. ORP measures whether a water stream is reducing or oxidizing. And the last webinar that we gave a couple weeks ago, that'll give you a good basic understanding of ORP if you didn't get to see that. Well, one problem that's fairly common is that many industrial RO units operate on drinking water, and drinking water is chlorinated. Well, polyamide thin film composites membranes can't take chlorine, so we either use activated carbon or ultraviolet irradiation or sulfite injection in order to remove the chlorine before it goes to the RO unit. Well, if you're using sulfite, then that's where an on-stream ORP meter makes sense. You can have a feedback loop that tells your sulfite injection pump how much to pump, and you can also have an alarm and a shutdown feature so that if the ORP goes too high, you can shut down the RO unit. Well, if you overfeed sulfite, you can end up with increased biofouling in the RO unit. So we would really like to minimize the amount of sulfite that's injected. If you can get an excess of maybe just a 0.5 milligram per liter, no more than 1 milligram per liter, then that's probably going to minimize the biofouling in the RO unit. So again, as far as using ORP as a troubleshooting tool, we want to make sure that the sulfite that's injected gives us a 0 total chlorine, but we also want a minimal sulfite overfeed. All right, so that's an introduction. Now let's move on to the bulk of the presentation and turn this over to Sherlyn.
Okay, thank you, ladies and gentlemen. Let me go ahead and show my screen here. Just to start off, to do what we to do this training presentation, to make it so that it's real live examples for you guys, I have my equipment, and the terms I'm going to use are are terms, but they're generic depending on whose instruments you have. So we're going to focus on how do you know for sure and how do you troubleshoot that that pH measurement that you're reading during your cleaning cycles is working or is accurate, is reading correctly, your analyzer and your sensor. And then the ORP system can be pretty much done the same way because remember they use the same reference. So the agenda, really quick, I'm just going to talk two things that I need you to get out of the pH basics, because if we don't understand or we don't realize two values, then when we go to look at our instrument and we're looking at how to troubleshoot our instrument, we don't know how to interpret those values that we're seeing, if they're good or if they're bad, okay? So we're just briefly on that. Then the bulk of what we're going to cover is when we go to site location or I go to site location or I'm on the phone with you and you call and you say your stuff's not working, you're seeing inaccurate readings, what's going on. These are the steps that I'm going to do with you or at site location. So our best practice of what to walk through. And then some real life pictures that I've seen with installations and what could be wrong, just to bring light to some things that you may see out in the field with yourself already. And then go over some typical complaints or commons or what could be causing them, okay? So that's the bulk of what we're going to do. Theory. All I want you to get out of this is we have the pH scale. We know it goes from 0 to 14. It's 7 is the neutral point. That means it's 0 millivolts. Anything below that, it's acidic. Anything alkaline of it. The biggest thing that we talked about that we highlighted is the effect of temperature. Remember, temperature is important to your pH regions for two reasons. There's two different types of temperature compensation. There is the effects of the glass electrode, and as the temperature increases, that glass will expand and contract, so it shortens the life of your system. But there's also one called a process temperature coefficient. That means outside of the glass changing, the pH of the sample actually changes with temperature. And the reason why we need to pay attention to temperature is because the Nernst equation has temperature right in it. So any effect of pH or any effect of temperature is very huge, is largely impacted on your actual pH measurement, okay? So out of this Nernst equation, what we want you to get out of it, the magic number, this 59.16 millivolts. That is what we want to stick in your head. At 25 degrees C, 59.16 millivolts is equivalent to one full pH shift. And this is important because when we look at those calibration data and what we're looking in the analyzer, correlating that value and what our instruments is offsetting or compensating back for. That's all we want you to get out of that theory. So the other thing about temperature is, remember I mentioned the Nernst compensation. Perfect slope pH glass electrode responds, one pH change is equivalent to 59.16 millivolts. Because of the way the glass is made, it actually will change with temperature. So the Nernst or automatic temperature compensation, or what we call Nernst compensation, changes and equates for this. So at higher temperatures or lower temperatures, that 59.16 millivolts is slightly different, okay? So that is what we just want you to remember out of the theory of pH. Now, you have an entire circuit in that electrode. It's an electric sum, and all we're measuring is the voltage potential, basically that U1 shown here, those hydrogen ions reacting on that glass electrode. Everything else, U2 through U5, should be equivalent to be 0. However, if that U5 gets coated, it's plugged, it's fouled, that will increase and change in your ORP measurement. You insert a solution ground electrode into your probe. That's what its purpose is. Then you can isolate and know, is what's going on affecting my glass for my process, or is it affecting my reference electrode? So that's one of the purposes of the solution ground rod, is to be able to differentiate where I'm having problems or where my process is actually affecting, what side of my probe that it's actually affecting. One thing I hate about most, to be honest, about pH is ground loop. Has anybody ever experienced ground loop problems in their plant? If we don't make sure that we have the analyzer, the pipe, and the probe all on the same, like liquid earth ground, the whole grounding, noise will travel up through our probe in that reference electrode into the analyzer, and it will shorten the life of our probe, and it will also cause noisy and inaccurate readings. So we need to make sure, and that's the other purpose of that solution ground rod, is that your sensors are on the same ground as your analyzer. So then we just need to make sure that our analyzer, that entire loop there, is on the same grounding of our process pipe. So this, I think, would be one of the biggest headaches, is trying to solve, especially if you're in Florida, is where I see it most common, ground loop currents. So that's the biggest headache with that aspect of it. And that's, from my knowledge and my understanding, that is really the stop of where we go. You can simulate in your analyzer on the terminal strip. There's going to be a solution ground terminal, and there's going to be a reference terminal. If you jumper, use a paper clip, use a wire, jumper those two together, and your reading locks on and it's no longer noisy, that is a good indication that you have improper grounding in your entire system going on. So that's one little test that you can run. Obviously, if you don't want to do that, you can easily just take a grab sample, take your sensor offline, and put it in the bucket. And obviously, if your system goes stable, and then you put it back online and your pH measurement or your ORP starts to drift again, that's another indication of grounding. So those are ways for you to figure out if grounding is causing your errors and your pH reading. So the bulk of where we're going to spend today. These are our steps on what we feel the best process is when we check your analyzer if you're having problems. So the first thing we're going to do is we're going to check the data in the analyzer itself. And remember, the photos that I have are just my instrument photos. For copyright issues, I can't use other people's equipment. Okay, the next thing, after I just look at what's inside my analyzer when I walk up to it right now, I'm going to try and simulate on the analyzer a pH 7 and a pH 4. This way it tells me, I can look and see if my analyzer is working or if I need to migrate and look at the sensor as the problem. And then if none of that works, I'm going to short, these are our terminal numbers, but it's your reference pin and your analyzer, your measuring glass, your pH measuring glass in the analyzer, and your solution ground. And all of those should lock in on a reading of 7. And if they don't lock in on a reading of 7, if it's like 3, 4, you know, whatever in your analyzer, then it's a good indication that your analyzer is actually what's causing your failures and what needs to be replaced. So right now I'm going to go into a little bit more detail of these 3 components, okay? We got some videos for you. So first, when you arrive at an analyzer, I said I just want you to take a look and see what you have. And when you call me, I'm going to ask you for some data. I'm going to ask you the last time you did a calibration, what was that zero offset or your asymmetry potential, or what are common terms? What's that millivolt? When you stuck it in that, you did your 2-point calibration, you stuck it in your 7 pH, how far off from 7 pH did your pH probe say it was? Remember, this example shows 11 millivolts. That Nernst value is 59.16 millivolts, remember? So at 11, not so bad. It's about 1/4 of a pH that we're compensating back in. But if we get to be about 30 to 35 millivolts, we're saying that instead of a pH of 7, my sensor is reading a 6.5 or a 7.5, depending on if it's a plus or a minus in that millivolt reading. So that's that purpose of that Nernst value of that 59.16 in the theory that we want to take back to. Okay. The next value is going to be the slope. Some instruments give it in percentages. Ours gives it in percentages. Others do give it in millivolts as well. But it's the same thing. That 59.16 is 100% slope. So this one is a 92% on this screenshot that we did here. So that's pretty good. That's not bad. But if we go below that, if it's about 85%, then we are going to look at saying, okay, well, I'm also having slow to read. So we need to look at probably fouling on the glass electrode is probably causing the issues. 2 other values that you get in your instrument are, we call them reference impedances, 1 and 2. One of these is our impedance on your glass electrode. One of them is the impedance on the reference electrode. So those values are in everybody's analyzers now. But we can read these values as well and figure out live time what's going on with the system as well. Other information that I'm probably going to ask you for that are in analyzers today are, when was the last time that it was calibrated previous like go 2, 3 back and show me that degradation. Give me those results out of the logbook, whether it's in the analyzer that you pull or your paper that you send, so I can see how quickly did it degrade and how quickly in between that calibration, because interpreting that data will help analyze how quickly the pH glass is being attacked or the reference electrode is being poisoned, okay? And then the other thing that we're going to look at is that temperature compensation. The top temperature compensation is normally what everybody calls just that ACT, the nurse, that's set to automatic and goes back to 25C. But we're also going to look at make sure that you don't have programmed in there a process temperature coefficient. On our analyzer, it's the bottom one shown there, to make sure that that's not what's causing errors or offsets in our pH values. So those are the data. So that's what we look at first. We just look and we collect that data. Okay, now the second thing that we're going to do is we're going to use a simulator. Hamilton sells a pH simulator that's in a box. Yokogawa used to sell one like back in the 80s, so I know they're out there. Sometimes they're in the field. They may not necessarily be in the instrument shop, but you can simulate on here a millivolt reading into the analyzer to say it's either 7 or 4, whatever pH value, and you look and see how does that display of the analyzer respond. If it matches, then we don't have an issue, but obviously if you're simulating a pH 7 to the analyzer and it reads a pH 2, then our analyzer is not reading that millivolt value correctly. Some people get this kind of simulation confused with the 4 to 20 milliamp output simulation. That's completely different. Obviously, that is just saying that my output on my 4 to 20 is scaling to my DCS or my PLC correctly. So this is the millivolt reading, the live reading into the analyzer itself that we're looking at. Okay, then the third one, I said on our terminals, you're going to short the reference, your measuring, and your liquid earth. And they should equal out to be about plus or minus 7 pH. And this is because when you short all those out, it should be a 0 millivolt reading, so the display should read 7 pH. If for some reason the display does not read 7 pH, it could read slightly like 6.8 or 7.2, because if you did your last calibration and you have that 0 offset, that millivolt value of, and I didn't realize I left the images there, sorry, in that video there, but it'll be that 11 millivolt offset will slightly change the reading a little bit. So it may not be right at 7, it'll be close to 7. Okay? The next thing we're going to look at is the cables and the liquid earth. Sometimes this is the last thing that we look at. We normally just say the probe isn't working, I calibrated, I cleaned it, doesn't work, I tossed it. We got to look at the connectors itself. So we need to look and make sure that they are actually dry, that they are wired correctly. If they're wired incorrectly, then it could cause issues. Our stuff has color coding that can get confused sometimes. I know a couple other people's have same kind of similar systems. So we'll just show you that. And then visualization checked, and then also check the resistance of the cable. Sometimes if the connector is not dry, you know, water will basically corrode it and it'll finally seep up into the analyzer and it could short out your analyzer. But we just need to make sure that they're dry, and sometimes we don't see this until we physically take the equipment out of process and hardline. Alrighty, so simple things. Where do we know, how do we know that our instruments are wired correctly? Obviously, most cables today are color-coded, and in the instruction manuals, whether you have a paper or online, you know, they'll tell you color here to this terminal kind of thing. There's online applications that help you figure out wiring as well. So a whole bunch of access, but basically we just need to get down to, is it wired correctly? And especially when we're trying to mix analyzers and sensors with competitors. It's easy to do that, but we just have to look at the documentation and make sure that we matched it up correctly, because my terminal 13 may not be the same purpose or serve the same purpose as someone else's terminal 13. So if you just look at my sensor wiring manual and it says, oh, this 13 is 13, but it's my reference and it's someone else's solution ground, we're going to get errors in our reading. So we just need to make sure that we match up the true raw reference, pH, solutions, shields, temperatures to the right terminals. That color code. this is where it kind of gets a little confusing. So there's an example here of where you have those individual 12 millimeters that have individual 2-wire cables, and they mean certain colors. And the purpose of that is when you have a sensor and you're 10, 15 meters away, so you're what's that, 30, 15, 30 feet away at any given time, you know that when you connect this sensor to this cable, it goes all the way through all your conduit wires and it's terminated at the right terminals in your analyzer. Here's an example where this can be wrong. Most of the time you'll see a red on a cable and a yellow on a sensor. For here, the image, I just showed you how they could be easily swapped. And if you don't match up the red to the red and the yellow to the yellow, if you have color coding, that kind of thing, then you'll get inaccurate readings in your analyzer display. So we just wanted to show that to you guys as well. So visual check of your sensors itself. We need to look, this is where it gets fun, for actual mechanical damage. We need to see what is the actual outside mantle could have been broken. Sometimes when we pull these cables through conduit and it gets stuck and then we kind of just pull it and knock it loose, we don't actually know that we've damaged it, unfortunately, until we rerun that 30 feet of cable all over again. It is a headache, but if we get down to the sensor's not working and we've replaced the sensor and it's still not working, we're going to have to pull that cable out and make sure that we didn't nick it when we pulled it through the conduit. Here's another one. You can shorten your pH cables. However, be careful when you do it because you got to make sure that you don't mess up the cable isolation and the grounding. Right here, they've used tape to kind of reseal where they've shortened it. So we just need to make sure that if you also do that, you seal it correctly, because any opening, especially if you're not in, you don't see, if you shortened it and then you don't seal it properly, the cable, moisture can ingress in that shortened cable as well. This one, take a look at this photo. I got two things here that we've seen with this cable when it was sent back to me from a customer that wasn't working. The top one I want you to look at is the top white. You can't really see it. Basically, all they did was they cut off the terminal pin and then shortened it back and stripped it back. That one's not necessarily going to cause as big of an issue. But look at the black cable at the bottom. They basically shortened it, somehow stripped it, and then put soldered iron to kind of seal it back into place. That right there is going to cause a big error in their measurement, because that's the shielding. In that particular case, it was the shielding cable. So they weren't getting actual proper grounding, so they weren't getting good readings in their measurement, obviously, because of not being grounded. So if we mess with a cable, just make sure we know what we're doing. We shorten it correctly. We pay attention to the ice. We don't damage the outer shield of your pH cable. And then obviously, this is another example of that conduit adapter running it through, and then it got pulled, and then after it sat there for a time, it worked for a time until its environment and process ingress started to eat away at the cable, and then finally it wicked through the cable all the way back to the terminal. And we don't see this. This is sometimes the last thing that we check. So how can we actually check the cables? I'm sure that you guys have probably already done this and you're more knowledgeable than I am, because frankly I'm not a huge fan of multimeters. But you can terminate on your cable the different points, whether it's individual, like these are those individual 12 millimeter, or if you have a varia pin, you can shorten on the varia pin the pin location to its mating end terminal, and they should be low resistance or high resistance if it's a shielding cable. So this is one good thing to look at if we don't want to rerun, if we're in a room and we don't want to run it through the conduit, but we have quick access on the panel, to the terminal or the sensor connection and the analyzer box, so you can easily match right there. It's one quick way to see if your cable was damaged when you ran it through the when it was run through the conduit and stuff. Here's another one that we need to look at, is just the inspection of the sensors itself. Okay, so sometimes you're going to get slow to respond, and we're going to have to look at how they're actually what happened to the process, because a lot of times we get, well, these were working just fine and now it's not working, the cable's fine, I changed the cable, I changed the sensor, but then when we go to change the sensor, that's when we see the visible damage to the probe. So if we start seeing slow to response, we need to look at it and pull it and see if it's coding or if it's kind of, maybe it's broken and it's having issues. And this is what I mean by saying how fast is it to respond to a process change. Physically, excuse the volume as we talk and do this, how fast does it actually respond when you go from a buffer solution of say 7 to 4 that you have on your grab sample? Is it pretty quick or is it slow? Is it bouncing around? If it's pretty quick, then you know when your reading is stable, then there's nothing that you probably need to do to it. But if it's slow and it's fluctuating, then we need to look at cleaning. If it's clean, then it's probably poisoning the reference, and that's what we need to look at. So just be cautious if you do these quick test things on how fast does it respond to see if it actually is using fresh buffers all the time. Okay. Here's another visual check. And this is one that you'll get inaccurate pH readings, but you won't see until you take the probe out of the process. Do you see the top left-hand side of this sensor here? It should have an internal KCl solution. Remember, you have a reference silver chloride pen immersed in KCl. In this particular example, there's no fill solution whatsoever. It is actually completely empty. So there's no continuity between your pH, your reference and your pH glass that's in your process and your actual reference pen. So you don't have continuity in the process. So that's a visual check. So we're going to see reading errors in our reading, but we're not going to know until we take the probe out of the process. Another thing that we can see here is, remember how I also said that there's different types of internal KCl solution. There's liquid, there's gelled, there's 1 molar, there's 3 molar, there's saturated. This particular sensor in this example is actually a gelled filled solution. So when we pulled it out, it's not just gelled inside, it's actually liquid. You can see that air bubble in there. That shouldn't be there. It should be a gelled solution. What this is indication is 2 things: higher temperatures and also process attack. If somehow you have a slight crack in your glass and there's an acid in your sample, and it gets into that KCl and it's a gelled, it can actually change it to a liquid form. When you change it to a liquid form, you get errors in your reading, you get drifting, and then you start having to recalibrate those errors out. So just pay attention. If you have a gelled KCl solution or KCl probe, it is still gelled, okay? Another thing that we see a lot of times is, anybody have high temperature applications? If you have high temperature, sometimes what can happen to the KCl solution is an effect called caramelization. It's just the higher temperatures physically change the white crystals brown. Doesn't necessarily mean that the pH probe is not working right now. It means that it's on its way to stop working. So if you see a brown electrode, it's not always bad. If it calibrates and it's operating, it's fine. You just need to prepare to go ahead and replace it shortly, because it will fail shortly. However, the picture on the right-hand side is a different type of caramelization or brown KCl solution, and this was actually caused by process ingress into the process, where the process actually attacked the KCl solution and reacted and changed it brown. So obviously you're going to see 2 different effects in your reading. One, you will not work, but the other one will actually work. It'll just kind of be drifting. It'll be off a little bit. It'll be when you do those 1-point process cals to the lab. Okay. Biggest one that's going to be the hardest thing for you to see when you're visual checking is hairline cracks. Remember, these are glass. They are sensitive. I've done it multiple times where I haven't paid attention. I've turned around and hit the pH sensor on something and just shattered the bulb. But then there's other times where you can tap it and then you go to put it in your pH 7 buffer, it reads 7. You put it in your 4, it reads 7. You put it in your 10, it reads 7. You put it in your sample, that should be 9, it reads 7. So a good indication, if you put it in a sample and it always reads 7, then you've got a hairline glass, and you may not actually be able to see it unless you're in perfect lighting at the right angle and it's clean because you don't have any process cover up on it. I mean, think of it if you're in a scrubber tower where you've got low lighting and you just took it out of that slurry mixture that you just wiped it off with a rag, and you try and tilt your glass electrode to see if a hairline crack. This is one that you may not be able to see, but you can remember, if you read 7, no matter what, your sensor is most likely cracked. Here's another one for visual checking. Remember those zero offset, those impedance values that we talked about. When those start to increase, that means your junction is being plugged. Those values on your display, you can actually read those and interpret those when coding's going on. However, if not, when you pull it out, this is one that you can actually see. These are examples of those wide body, most commonly used sensors. That entire picture on the left, that whole white section around the glass and the solution ground temperature electrode is the junction. It's supposed to be white. The picture on the right was when it came out of a process and it was completely black. And they were getting inaccurate readings. They were having to recalibrate it every hour, and they couldn't figure out why. They gave the data, and I said, well, it really looks like this. When we went out to the site location, we pulled it out, and I said, oh, yeah, that's not supposed to be black. And they're like, what do you mean? We soaked it in some HCl for just a couple minutes, and it became white again, and it started working. So this is one indication. If you know how to interpret those data, that zero offset when you do that calibration, and those impedance values that you get when you do a calibration, you can know if your junction's being plugged. Most instruments today have alarms, and what I find is people are actually turning off, or they have turned the alarms off because they were, annoyances to them. They didn't know what they were doing. They didn't know how to interpret them. They were just going off. They didn't want them. This is a picture of literally a set of probes inside of a salt bath where they turned off all the alarms, and it was still reading because you can see the glass electrodes were just fine, but when we physically went to go take it out of the process, that much salt was built up on the actual probes. So eventually their pH reading started to drift, and it was simply because of coding. So leave those alarms on your analyzer that the manufacturers have that give you indication on coding ingress, okay? That can help you know when you've got to clean it before it gets and it's failed. Another alarm that they have in them is when your glass breaks. A lot of times people will say, my reading's fine, and then all of a sudden it doesn't read, I can't do it, I'm trying to do a 1-point process cal, it still doesn't work, and we pull it out and you see that the pH glass bulb is completely missing off the probe. At that point, there's really nothing we can do but change that electrode. So leave those alarms if you can on so that you can get an indication of when your sensor's cracked or when it's starting to foul that junction and everything, okay? My favorite one, another thing with gel electrodes. They're kind of a little pain, but manufacturers' boxes have arrows on the boxes with the recommendation for your storage, because you guys should all have one pH probe for the most part of your very critical processes sitting on your shelf in your plant that you can pull when your process sample goes down. Gels are notorious for this. Remember, gel expands and contracts with pressure and temperature. So when they fill the glass electrodes up, you have to leave a little bit of an air bubble in there so that the gel has someplace to go. Otherwise, if there's not a little air capacity in there and it expands, it'll shatter from the inside out, okay? So when you store these either on the side, like these pictures are, or you store them with the bulbs pointing all the way up to the sky, that gel is going to migrate towards the center of the earth, towards gravity, and that air bubble is going to come down. So a lot of times you get complaints where there's nothing in this solution, I just got it out of the box. And this is what we have to ask is, how did you store it? You have two options. You can either A, just let it sit, like in a, take it out and let it sit with the bulb pointing towards the center of the earth, 24 hours to let it migrate, or you can actually hold the glass electrode and shake it, and shake the gel that's migrated up back into the bottom of the probe. Obviously, I've done this before. I've shook it, and actually didn't have a good grip, and the probe went flying. So just be careful that you aren't sitting next to a desk where you can hit it on a desk or a railing, and then B, you don't lose the electrode while you're shaking it. Okay. One thing that people, it's like the last thing people think to check. Your system has a temperature electrode, and remember, temperature is in the pH calculation. So if your temperature portion of your probe is not working, you're going to get errors in your pH measurement. So a lot of places have resistant boxes, and there's chart values out there that say, okay, this much ohm resistance is equal to this much temperature reading. So it's a good indication for you just to check to make sure that the temperature element in your system is working correctly, is reading correctly. We basically say that if it's within 0.3 degrees difference, then it's okay. Outside of that, nope, we need to look at replacing that temperature electrode. And that is pretty much the last portion of what normal people go to check, okay? Normally it's the cable that goes or the sensor's bad itself. All right, so I'm right at the 30-minute mark, so we're going to now go into, we've troubleshooted the instruments, they work correctly, the probe is correct. We also need to troubleshoot the process, because sometimes we need to make sure that A, it's installed correctly, B, the equipment used is the right equipment for the application, and C, it's even within the process specifications of the process. This picture here I show you is one where I know what my equipment looks like. So that junction, that black, you see white, black, white, that back white and that black band should be up inside that black body. So this is one where the process pressure actually affected and pushed out the junction from the electrode, and then the process was able to ingress into the back side of that, into the sensor, and it damaged the sensor. So this is one where the specification was not right for the equipment being used, okay? So here's some things that we look at. We're going to look at the basic pressure, temperature, pH range, and I can't even talk today, I'm sorry, composition. You know, we're going to look for if there's HF or if there's sodium hydroxides, if there's sulfides in there. HF obviously is really aggressive, especially when you get with the lower temperatures. It'll eat the glass. Doesn't matter whose electrode, it eats the glass. So we need to make sure that we don't have just like a general purpose. Remember, we're going to put something that has a thicker glass membrane on there. Same thing with sodium hydroxide, so we get a longer life. If we have a lot of sulfides in our process, they can actually react with the silver chloride reference pin and form a solid. So we want to make sure if we've got a process with high sulfides that we actually use something like a flowing junction that keeps the process from getting in that junction and possibly into the reference system to attack it. So either that or something with like a KCl reservoir. Remember, where you can put the process in a KCl tank, or the reference electrode in a KCl tank, so the process has to get all the way through into that tank and attack all the KCl before it gets to the probe. So there's things that we need to look at there, okay? The last thing that we're going to need to look at is any recent changes. These may be minor changes to you, but they can really affect the life of your probe. Take an example like a CIP application. You were cleaning for 30 minutes at 130 C. You simply just changed it to 10 minutes at 140. But we didn't look to make sure that the sensor that we're using can hold up to that life. And now it lasts about a week. So little changes, and if we don't have the right instruments in the process, can affect in the long, big scheme of things, okay? When we look at the installation, we're going to look at, is it before or after dosing? Look and make sure it's not in a pipe where there could be no flow, or what we call dead time. You know, it's not in a solution. If your noises, your pH is reading, is moving, could be because it's not physically in solution. Same thing if you're near an air bubble, does the flow forming air bubbles that can cause your readings in your pH. Flow, for the most part, we say is about 6 meters per second is good. However, if you're in low ionic, you need to make sure that it's lower than that, because you need to make that continuity, because there's no ions in your pure water, so you need really low flow. And then again, make sure we've got the right glass composition for the process. Here's one to look at from a nickel application. Here's this example of a mining where they have the probe and it's pretty much in line with the T, but it's not all the way in the process. And they had heavy scaling that actually happened in the pipe, and it was so bad that it actually pulled and plugged the prong around the sensor glass. So they weren't getting pH measurement at all. So this is one where we pull it out and we visually check to make sure that maybe we need to move it somewhere else where we can easily take it out and clean it more frequently, or you need to add an online cleaning. So take a look at stuff like that. Here's another one I just want to point out because I'm running out of time. This picture here is a panel that was purchased, and if you see here, the flow on a flow meter is supposed to go, or flow fitting is supposed to go from the bottom to the top. That way your glass electrode is always maintained and like a full solution. This one goes straight from left to right. You're not going to get good recirc of your sample around that pH glass in there. So be sure you plumb correctly, bottom out the top. Another thing here is if you don't know what these 12 millimeter glass electrodes is, you can kind of see that glass. When the installer installed this flow fitting, they actually installed the pH electrode inside its wet boot. This is very common. You're going to get pH readings, and they're not going to change with your process because it's inside of a standard KCl solution. So make sure that we take off those fittings. You'll see these, and we're going to have to skim through them quickly. Water ingress, visually check. You know, you're going to get alarms if you don't turn them off before you get to this point, but you can visually see this. So we call it wet feet. When we're mixing and matching cables and sensors, we need to make sure that we don't damage, obviously, the cable again, and make sure we're using jumpers that aren't corroded. If we're using jumpers that are corroded, you're not getting good continuity, so you're going to get errors in your reading. So basically looking for those kinds of things. Then I have another picture real quick of those. This is our equipment again. The wet boot, people were using them as the actual image on the top is you have an O-ring that's red and a spacer. When you put that in our holder, you get good continuity. It seals. Everything pushes down on each other. What they did is they used the rubber footing that goes on that wet boot as the O-ring, and it didn't seal, and it got ingress, and it went all the way up into the process and got into the analyzer. So we just need to make sure we got all the right O-rings. So here's common complaints that we have, and then we'll open it for question and answers real quick, okay? Because it's a lot of information, and you can get into a lot of details when you try and troubleshooting. So to get it in a short period of time, sorry, kind of skim over it. But basically, if your sensor's not responding to changes, we need to make sure visually, obviously, that it's not broken, wiring's correctly, there's no moisture. Remember that diagnostic data, I'm going to ask you for that. We can read it and interpret it and kind of quickly go what's wrong with our system. Other most high common complaint is it's unstable, difficult to calibrate. Incorrect wiring, no solution ground. Remember, if you don't have good grounding, you get noise that goes all the way up into the pH measurement, unstable reading, okay? So we can jumper those together, our reference and your solution ground together, and that will lock in and give you stable reading. If you don't want any alarms, then you can leave it like that, but it's not ideal. Just make sure you can kind of ground the whole system. And then scaling. And again, leave those alarms. They'll help you turned on in the analyzers for you guys. So that is the high level of what I have without going in too much detail. So to open it for question and answer, I think that's right at almost 40 minutes. Went over a little bit. Sorry, guys. And then if we have questions, and then obviously anytime that there are other questions that come up, you know, we can always give more details too.
Okay, thank you so much, Sherlyn. Excellent presentation. Now Sherlyn will be doing question and answer. So she'll say the question and then give the answer. Again, if we don't cover your question, it'll be sent to you by email. Sherlyn?
Okay, so the first question here is, how does the uninstallation and installation of a pH sensor happen when it's being replaced with harsh liquid properties? Okay, the term and the question don't make sense to me. The uninstallation and installation of a pH sensor, you're physically meaning you pull it out and put it in? Or can you give a little bit more? You could be talking about the process coming ingress into the sensor. Yep, I can also answer it by email, but if you're asking about the process ingressing into the sensor itself, normally that's what we call pumping effect, and that's caused by changes in pressure and temperature, and that KCl solution actually expanding because the temperature increases around it. So it will suck the process in and then, you know, pump it back in and pump it out, and that will affect the KCl. What are the differences and or advantages of the glass wands versus stainless steel? Glass wand, I don't know what a glass wand is because we don't have any glass wands. We have 12 millimeter electrodes that would be glass, but then the stainless steel is holders. So I can look into what a glass wand is for you. In cold environment, how to maintain the optimal outside temperature of the sensor in order to read accurate readings. A lot of times in places, you know, I say in north of Georgia because everywhere else it gets cold, but here they actually will do like a heat wrap band around the sample system itself. So either it's in an extracted device and an enclosure that has a controller on it, or just like a pipe heating band around the housing material. And that's really important because if you are cold and you have a glass electrode that's exposed to, like, say, Canada temperatures and it's not heat traced, then your glass electrode's going to shatter. Okay, when you ask the question, when should we use a jumper? So pH systems, there's two portions. There's a reference, which is considered a low impedance system, like a electrode, and then you have the measuring glass, which is a high impedance. Normally the jumper, when you're actually wiring it like initially in an analyzer, most analyzers have the ability to do either dual sensors that have dual high impedance or a low and a high. So we'll have you put the jumper in for your reference to tell the analyzer, hey, that's a low impedance. The other time, if this could be asking when do you use the jumper, is if you need to figure out if grounding is your issue. If you're noisy reading and you want to quickly just say, is grounding causing my errors, then you can terminate with a jumper your reference in your terminal and your solution ground. And if your pH measurement goes on for that, then you can, that's an indication of grounding being your issue. But like I said, it's not recommended. You can leave it there, but it's not good practice. It's better to solve the grounding issue. So next question is, when reference gel is compromised, can the gel be replaced and work properly again? It depends on what type. If it's a gel filled, most of these are not refillable, but some probes are rebuildable, is what they call it, where you can physically pull out the reference portion and put a new one in. So depending on your system, you may or may not be able to do that. All right, next question is it possible to use a pH sensor for as ORP? Yes and no, depending on the sensor that you have. If you have a sensor that has the capability, meaning most of the time they'll use a solution ground, the temperature element in the wide body sensors, which you see it in, has a platinum pin that they're using to do the temperature and the solution ground. Because it's platinum, it's a noble metal, you can do pH and ORP out of the same probe. But some wide body sensors use titanium, and then that's not good practice because it's not a noble metal, so you can't get an accurate ORP measurement. So it is possible. Okay, if you have a pH and ORP sensor in line, do you only solution ground one probe, or do both probes need that solution reference ran back to the controller? Okay, two different types of answers here. One is if it's a combination where the solution ground rod is your ORP, then in the instrument, the analyzer, it's terminated at your solution ground and it's acting as both your ORP and your solution ground. And you've just changed the electronics to say, hey, this is reading pH and ORP, and in the background, it does it all for you. Okay, if you have two independent setups where one is pH, yes, you have to have solution ground. And if you have one for ORP, it is good practice to have a solution ground with your ORP as well. Because remember, with your ORP, you're using that standard KCL reference. So any ground loop issues are going to go right through that reference probe as well. So I hope that answers it. Alrighty, next question is a long one. So given fluctuations in temperatures of the solution, should you replace the reference electrode or replace any solutions in the electrode? For instance, if the bulb or reference becomes empty due to loss of solution through temperature fluctuations. If so, is there a time period like every half year to replace these? Okay. If you have temperature fluctuations and your solution, your electrode is being depleted the KCL, you actually want to look at using a completely different reference system than what you're using. That's going to be the best practice and give you the longest life. They have systems that what we call, common term is kind of flowing reference is what they use them as. They have a port that's open to the process and they're attached to some external reservoir tank that has overhead pressure that you maintain 10 psi over your process pressure, so that KCL is always flowing out of the sensor so that the process doesn't come in and suction it out. So if we are getting emptying of our sensor, then most likely, and it's frequently, it's quickly, like every 3 months, or even shorter than that, then absolutely you don't have the right reference for what the process conditions are. Alrighty, and it looks like that was the last question, so I'll turn this back over to you, David. I hope you guys got a little bit of information, and like I said, it's hard to do pH troubleshooting in a quick hour because there's so many different variables, so we're always here for questions if you need help.
Thanks, Sherlyn. Great job. Just to wrap up then, well, as I said, you're going to be able to go to our website, look at a recording of this webinar so you can go over this information, because that was a lot of information, a lot of great information, but it's a lot. May have to look at it more than once. As far as us, we are your training professionals, so if there's anything that we can do for you in the training area, please let us know. We do have a chemical cleaning for RO unit in Tampa, Florida this September that you might be interested in. And also we provide technical services if you didn't know about that. So anything that we can do to help you out, we'd love to do it. So thank you so much for attending. As you're leaving, you're asked to just give 3 polling questions that really will not take any time. It's really just to give us feedback on how valuable this webinar was. So thanks so much, and we'll see you at the next one. Bye-bye.